Today I'm going to explain to you about electron diffraction. Now this was an idea proposed in the 1920s by the fabulously named Louis Victor Pierre Raymond de Broglie. He's a French aristocrat and brilliant physicist. And as part of his PhD thesis, he looked into the idea of electrons and matter being both a wave and a particle. Now, of course, at the time, 1920s, Einstein had explained the photoelectric effect in terms of the particle behaviour of light. And of course, from 1801, Young slits onwards, everybody thought light was a wave. The photoelectric effect suggested otherwise. And the physicists at the time were just coming around to this idea that light had these strange dual properties, particle, wave, who can tell, depends on what day it is, what experiment's going on. So de Broglie, he suggested that these particles, electrons, etc. could also be wave-like, and so he set out to prove this. And to do so, he used equipment like this, which is an electron diffraction tube, and I'll explain you through the process, show you what's going on, and hopefully, well, we will see electron diffraction after that. So let's look at the equipment in a bit more detail. We have a 5,000 volt supply here. With low voltage output, these two yellow cables, 6 volts AC, and they're connected to a filament lamp, just a small filament like in a torch bulb, which is in the back here. You won't be able to see it unless I turn all the lights out, and we don't need to do that. But there's a small filament lamp in there. Now that filament is very hot, glowing red, and the idea is we're producing a sort of a cloud of electrons around it. So because it's so hot, the electrons in the metal, they can be ionised, they can escape, they can, they can go wherever they want, but of course they stay around about the filament. There's a little fuzz around it, it's called fermionic emission. What we then need to do is to accelerate the electrons that have escaped from that filament at great velocity towards our target, which is further along the equipment here. And to do that, we have these high voltage cables. If I connect the negative to the filament, so that's the same filament that's glowing here, and then connect to a small tube here, which I'll show you in more detail in a moment, the other end, the 5,000 volt supply, I can supply a very high voltage to this little tube here. So let's look at that in more detail. So here is our equipment close up. Right down the bottom there is the filament, which you can't quite see. If I use my laser pen, it's sort of there where that's red. That's where the filament is, and that's obviously connected to the negative supply as well. Now the business end, so to speak, is that tube in front of you. Whoops, that tube in front of you, that small tube there, that one, and this is a hollow tube, as you can see. Now that's connected to the very high voltage positive, you can see it there, the very high positive voltage. And it means the electrons, which are buzzing round about the filament down the bottom there, come hurtling towards that little tube there. They're achieved a massive velocity by the time they get there, 10 to the 6, 10 to the 7 metres per second, easy calculated. And they then hit that target, that small little circular target, which you can just about see there. That is a piece of graphite, very, very thin piece of graphite. There it is from the front. Not the best of views, but you can just about see it again. There, that's the target just in the middle. So our graphite target has a specific structure, which is why graphite's chosen. Graphite, as you should know, is a form of carbon, and it's carbon where the atoms are sort of tightly bonded to 3 others, and then they're sort of bonded in a hexagonal shape in a plane, a flat plane. So you've got like hexagonal arrangement of your atoms spaced out in a plane. They're quite strong bonds, and then you've got another plane on top, another plane on top, another plane on top, with quite weak bonds between those, which is why graphite can slide. So the important thing for us for our electron diffraction is with the atoms sort of spaced out here, 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 whatever, there's gaps in between. And obviously with diffraction, we need to have a gap to diffract our waves through, and that's what we're going to be firing our electrons at to see if we can get a diffraction pattern. However, how will we know we've got a diffraction pattern? What will it look like? How do we understand what we're actually seeing? And to understand that, what I'm going to do is show you another piece of equipment over here with an explanation of what we're seeing, how we're seeing it, what exactly is happening, and hopefully we'll enable me to prove to you beyond any doubt that electrons are actually diffracting, they are actually waves. So let's go and have a look over there. So here's the setup to try to explain what we're going to see in our electron diffraction tube. We have obviously over here a laser, a light source, to produce our waves, and we have here a very fine grid in the centre of this aluminium disc which can rotate round. The disc is irrelevant, it's just to help it rotate, as you'll see, and then over there is a screen. So we can turn our laser on and we get a laser beam pointing down at the gauze. Oops, got my camera in the way. And that appears and gives a clear diffraction pattern on the screen. I'll turn the lights off later and show you how that looks. So, this is a model of the graphite in here, the thin piece of graphite which we're going to fire electrons through in a moment or two. And as I said, the graphite is like a grid. It's a very thin layer with the atoms spaced out in hexagonal shape with another layer on top, another layer on top. So our fine gauze, which you can see at the centre of here, is basically going to have the laser beam travelling through that gauze, causing a diffraction pattern. And it's acting as if we had one layer of graphite and we can see the pattern on the screen. But unfortunately, we can't have one layer of graphite. There's no way we can get graphite one layer thick into a tiny little target here. It just can't be done. So, in effect, what's happening in there is the atoms will be orientated one way, then another, then another, then another. So to help demonstrate the effect we're actually going to see, imagine this is the orientation of one plane. We're in sort of, there's your plane and the light's coming through. We could have one plane could be in that orientation, the next one could be in that orientation, that orientation, that orientation, that orientation. And by putting this in lots of different positions, we can see all the different orientations. However, as our electrons are going to go straight through all these multiple layers, we haven't got many, but there's a lot. Basically, we can show that by putting the laser beam through here, looking at the pattern, and then spinning that round, and then that will give the effect of the light will go through in that position, that position, that position, will all be superimposed on top of each other, and we can actually see the diffraction pattern you would see from multiple layers of graphite. So I will demonstrate this with a laser beam first, so that you can actually see what shape you would get, what pattern you'll get, and then we'll come back to look at this equipment here and see what it looks like. So let's go and see the effect of this, and I'll make it a bit darker now, so we can actually see the diffraction pattern really well. Okay, let's go over and have a look. So here's the laser light diffraction pattern as it's passing through the gauze in one position. And of course it can go through that position, that position, that position, that position, all these different positions depending on the orientation of the gauze, or for our experiment, the orientation of the sheets of graphite. Now, and if I spin this, you will see the effect of the pattern you would expect to see if you have got multiple sheets. It's quite clear. You've got a bright point in the middle and rings around the outside where the adding together of the different diffraction patterns are clearly shown. So if we have electron diffraction through our multiple sheets, we should see something like that. Let's go and see. So here we have the apparatus set up with a little green dot in the centre of the screen. And I'm going to increase the accelerating PD, and you'll see it becoming far greener and greener and greener as more electrons hit it. And as I get to a certain amount, you'll just start to notice some concentric rings appearing. They're quite faint on my camera, but they're showing up quite well. The dot in the centre has become much larger on the screen. That's a camera effect. It isn't quite like that on the actual screen I'm looking at. Now we're seeing a clear diffraction pattern, clear concentric rings, just like I showed you with the laser. I'm going to turn the PD up. It goes a bit wilder in the middle, but you can see the rings quite clearly now. Now that pattern is just like I showed you on the screen with the laser as the light travels through the gauze. In this case, we've got electrons travelling through our graphite gauze, in effect, and being deflected or diffracted onto the screen, and we see these concentric rings. Now, you could argue that then it doesn't prove the wave nature of electrons, because they could just be taking whatever route they can get through all the gaps and through the layers and just appearing in those positions due to the actual orientation of the atoms. But there is a key thing which proves this. De Broglie was very clear in his theory for his PhD. He said that as you increase the speed or momentum of the electrons, their wavelengths will get shorter and shorter and shorter. Well, the gap between the atoms stays the same, so if we increase the voltage and the wavelength gets shorter, then the diffraction should appear less. So let's see. I'll turn it up. And the rings get closer and closer because the diffraction is less. I turn the voltage down and they get further and further apart because the diffraction is more as the wavelength gets longer. And you cannot explain what you're seeing on that screen in terms of particles. Just like with young slits, we couldn't explain that in terms of particles. You can't explain this in terms of particles. We are showing diffraction of electrons. Electrons are behaving like waves in this experiment. They are waves. They are particles. They're both. And that's the way the world seems to be built. Okay, I hope you're convinced that that is electron diffraction and that electrons really are waves.